Hello and welcome to um, Voltaic Cells 14.2. So we're going to have this in two installments. Those are going to be part one and part two. So right now we're just going to look at part one. And for part one, we're just going to take a look at what a voltaic cell is, how to figure out the anode, the cathode, and good stuff like that. Okay, so as you can see here, a voltaic cell, from what you've known before, it has two different electrodes. You have an electrolyte, and you have a movement of electrons. Now you also know that electrons move from the anode to the cathode. And here's your movement of electrons. And now what we're going to work on today is just looking at why it moves from the anode to the cathode. What is going on in order for that to happen? So the first electric cells were more for practical purpose of generating electrical current than scientific study. And to better understand the science behind the operation of a cell, chemists use a cell that has two electrodes and their electrolytes separated. So there's two containers. Each of the electrolytes are in the containers, right? And then you have an electrode here and an electrode over here. You have this thing called the salt bridge. And in the salt bridge, you have a movement of ions, okay? Depending on what's in what half, the cations and the anions are going to split up, but we'll talk about that later. And these are attached to some kind of device that measures voltage. And they also look like this, where you have this thing called a porous cup. This porous cup also has an electrolyte in it. This is opaque white, and you have a beaker with an electrolyte as well. So these two are pretty much the same, except they look differently. It's just a different apparatus. A porous boundary allows ions to exchange between the two electrolytes, but prevents them from mixing. So this porous cup actually allows ions in and out. So a voltaic cell is an arrangement of two half cells separated by a porous boundary, especially suitable for scientific study. So here's another example, more so articulated a little bit better. You have your, in this case, a copper electrode, a zinc electrode. You have your electrolyte, which is zinc nitrate. And you also have a copper 2 nitrate electrolyte. And you have this salt bridge that has, now this for example, NaNO3 is what's going to be transported in and out. Now this, you don't have to memorize, it's kind of arbitrary. At the end of the day, what you have to know is where the cations go and where the anions go via this salt bridge. So this is kind of like a little kind of road. And remember, cations are positively charged ions, and anions are negatively charged ions. So this diagram and this up here, they're saying the same thing, okay? So here's it's saying on one side there's zinc and there's the electrolyte, and on the other side there's copper and the copper nitrate, and this is telling you that it's divided. So this right here is saying, oh, it's half here, half over here. But I'll talk about that more in detail in a bit. Each half cell consists of an electrode and an electrolyte, obviously. So how do we determine where the anode and the cathode is from this example for this right here? How do we know where the anode is and the cathode is? Okay, I'm going to walk you through that. So here are my entities. The first thing you're going to do is you're going to list all your entities. So we have copper, solid, copper ion. We have silver ion and silver solid. Also, because of this, we actually have H2O. But it's not a thing. Like I'll kind of find it over here. Water is somewhere in here, but it's not part of the SOA or the SRA. So we're going to locate the entities on the redox table. So here's our silver metal, here's our silver ion, here's our copper ion, and here's our copper metal. Okay, so once you've decided that, you have to figure out where is your SOA and your SRA. As you recall, For an SOA, it's the highest on your left, and your SRA is your lowest on the right-hand side of the table. So once you figured that out, then you can actually write each half reaction, and you can write it all out. The strongest oxidizing agent present in the cell always undergoes a reduction at the cathode, as you know, and for the strongest reducing agent, it's what's being oxidized. So at the cathode, we have a half reaction. Electrons enter the cathode via the wire. So as you can see here, okay, it's using up electrons. The silver ions are removed from the solution and converted to silver metal. An electron increases in size. This is really important, kiddos. Okay, so what's happening is that you're actually producing silver because you're taking the silver from the electrolyte, the silver nitrate. You are getting the electrons from the anode, and you're going, okay, I'm going to take my silver ions, I'm going to attach it to an electron, for lack of a better term, and I'm going to create silver. And this silver actually attaches itself to the electrode. And you actually get an increase the size of your electrode. To maintain electrical neutrality, cations move through the salt bridge to the cathode. Cations are moving via the salt bridge to the cathode, and I'll explain why that is in just a little bit. So the strongest reducing agent present in the cell always undergoes an oxidation at the anode. So let's take a look at what's happening at the anode, kiddos, shall we? At the anodes, it's producing electrons. So because at the anode it's producing electrons, right, because it's going through oxidation, it's producing electrons. Those electrons then go through the wire to the other side, to the other half, and then the electrons are used for the other half reaction. So electrons leave the anode through the wire because they're being produced at the anode. Copper metal is converted to copper ions in solution, so the electrode decreases in size. Basically what's happening is it starts to break down. So this copper is coming from the electrode. The copper is starting to break down into copper 2 ions plus 2 electrons. So it's using up the copper in order for that to happen. So what's happening to the electrode? It's starting to break down, and all of a sudden it's turning blue. The electrolyte is turning blue because of the, oops, can't spell, because of the presence of copper 2 ions. If you use your data booklet, that copper 2 ions in solution look blue. To maintain electrical neutrality, this is important, ions move through the salt bridge to the anode. And remember, anions are negatively charged ions, and cations are positively charged ions, and they move to the cathode. So here we have the one half reaction, here we have the other half reaction, and we have to make sure to remember that you want to make those electrons the same. So we're going to multiply this whole half reaction by 2 so that we can then cancel out the electrons, and we get our net ionic equation. Okay, that's pretty much how we do things. The salt bridge again is super necessary, and I'll explain why right away. So the purpose of the salt bridge is not to move electrons from the electrolyte just arbitrarily, rather it's to maintain charge balance. So we need to make sure that things stay neutral, okay, because the electrons are moving from one half to the other. So as we know in the anode, let's compare the anode to the cathode. At the anode, electrons are being produced. They are moving via this wire to this half, right? So what's going on when that happens? The electrons flow from the anode to the cathode, we know this. Oxidation reaction that occurs at the anode generates electrons, and that's why there's a movement, and positively charged ions. Where is this coming from? Okay, so if we take a look over here again, okay, these electrons here are moving via the wire. So what's going to happen is you're going to get a lot of extra Zn2+ being made. That's going to cause this half to be positively charged, and we don't want that. We want it neutral. That's why we have anions, so a negatively charged ion, to go into this half so that it balances off the 2+. Does that make sense? And then that solution becomes neutral. So that's why that is. So in order to maintain neutrality, the negatively charged ions in the salt bridge will migrate to the into the anode half cell. Okay, so you don't have to memorize what this is. Like this is NO3 minus. That could be anything. And this is potassium ions. That's just because in the electrolyte there's also, or in the salt bridge, or typically in the electrolyte you have potassium nitrate. You don't have to know that. All you have to know is this. Ions, negative ions or anions, move towards the anode, and the positively charged ions or the cations move toward the cathode. And they start with the same 3 letters. So cations move to the cathode, and anions move to the anode. Cations are positive, anions are negative ions, right? And these are positive ions. So that's all you need to know. And you don't need to know what they are. You just need to know that's where they go. Just cell notation, drawing cells all the time can be tiring. Sometimes, or scientists come up with something called cell notation, which is basically this. So that we start off with at the anode. And you don't need to, like, you can figure out where the anode and the cathode is just by using your redox table. But this straight vertical line, and I'm kind of reviewing, indicates a change of state between solid and electrolyte. And we have another one of these. And we have our boundary, right? So indicates a porous barrier. Will let ions through but prevent mixing of solutions, such as the salt bridge. So this thing here separates, is saying that it's in 2 different halves. So this is half a cell. This is the other half a cell. So let's summarize. We have our anode. This is where electrons are being produced, right? These electrons then move via the wire into the cathode, okay? And another thing that you have to know is that we have cations moving to the cathode, anions moving to the anode in order to make sure everything's neutral. And then we have our anode. This is for the kind of like the short version of the whole drawing. You have the anode, and then saying that there's the electrolyte for the anode. This is the division saying, okay, there's half of the cells. Then you have your electrolyte plus your cathode. So voltaic cells with inert electrodes. So sometimes you're going to get an inert electrode, which means in this case here, for example, you have copper. Oh, copper is not the inert. The carbon is in. This you can't find in the redox table. It's not a thing. It actually doesn't go through redox. It's just there to kind of hold a place. Okay, so when you have that, what you have to do is you just have to kind of change your thinking a little bit and use your electrolyte as one of the electrodes. So inert electrodes are used in voltaic cells where the oxidizing or reducing agent is not a solid metal. Okay, it is actually the electrolyte, and I'll show you that really quickly. So they provide a location to connect a wire and a surface on which a half reaction can occur. That's its only purpose. It does not serve as an electron maker, or it doesn't use up the electrons for itself, just for the electrolyte. So here's an example. Write equations for the half reactions and the overall reaction that occur in the following cell. So this is the cell we're talking about. We're going to list our entities, and I'll show you on the other page here. So here we are. Here's all of our entities. Now I'm going to find them again. This time we have not a metal electrode. We have, because we have an inert electrode, we're actually using the electrolyte. We found it. It's right here. The chromate ions are there. And also we have the copper is still here, and the copper ions is here. Now, like I said, even though water is one of the entities. If you look for it in the table, it's not going to be your SOA or your SRA, so I didn't bother including it. But you're more than welcome to figure that out on your own. Okay, so locate all the entities, determine the SOA and the SRA. So at the cathode, we determined that here is our SOA, and for the anode, your SRA we determined is the copper. Now remember, we have to make sure that the electrons are balanced, so we have to multiply in this case by a coefficient of 3, and then they cancel out, and here's your net equation. So it's kind of fun. So here's a little example. Write equations for the half reactions and the overall reaction that will occur in the following cell. So you're going to list all of your entities. Okay. Now what you're going to notice too, there's in this case here, there's an inert electrode. Oh, look at this. There's another inert electrode. So we're going to strictly look at your electrolytes. So here is our SRA, and here is our SOA, and you're going to go ahead and list them at the cathode, at the anode. Remember, you have to balance your electrons, okay? So you multiply by a coefficient of 6, that cancels these out, and there's your net equation. And also to draw it out, you just have to decide where your anode is. In this case here, you're looking at the anode and the cathode. You're looking at your electrolytes, not at your electrodes, because they happen to be both inert. Also, you have to tell me where the cations are going, towards the cathode. Your anions are going towards your anode. Here's your anode, kiddos. So you have to also show the movement of electrons. And that's about it. So good luck going through this. I'll post some practice a little later after part 2, but have a good day.